Have you ever really stopped to wonder how a simple curved piece of glass can capture this massive landscape or, a super detailed portrait? It really does feel like magic, but nope, it's all physics. So today, we're going to pull back the curtain on the lens. We're going to break down exactly how it bends light to create the images that, well, shape our world. All right, let's get into it.
Okay, so this is the big question, right? How in the world does a lens take all this scattered light coming from an object and somehow wrangle it into a perfectly sharp, focused image? It's a pretty amazing journey, from the really deep physics of light down to the simple rules we use every single day in our cameras and even our eyeglasses. And you know what? We're going to walk through it, step by step.
All right, here's the game plan. First, we'll look at how light bends twice. Then, we'll tackle something called the lens maker's formula, and then simplify it way down to the thin lens formula. After that, a cool visual trick called ray tracing. We'll even solve a magician's trick with magnification, and then we'll wrap it all up with your own lens formula toolkit.
Okay, first things first. What's the fundamental secret of every single lens out there? Well, it's not one action, it's two. A lens works by refracting. That's just a fancy word for bending light as it enters the glass, and then it bends it again as it leaves. Seriously, this double bend, it's the key to absolutely everything.
So let's start with the big picture here. You've got light traveling from an object, we'll just call it O. It passes through this convex lens, and boom, it forms a focused image on the other side, which we'll call I. Our whole mission right now is to figure out the physics that's making this happen right inside that little piece of glass. Okay, now let's zoom right in on that first surface. When the light from our object hits the lens, it bends. Why? Because it's slowing down as it goes from the air into the much denser glass. This first bend creates something physicists call a virtual image, right there at point I1. Just think of it like a temporary waypoint, a point the light looks like it's coming from. We're going to need that for the next step.
And of course, there's a formula for that. Physics has an equation for everything, right? Now don't worry about memorizing this thing. The important part is just what it does. It connects the object's distance, u, and that virtual image's distance, v1, with the curve of the lens, r1, and the type of glass it's made of. It's basically the math behind that very first bend. Okay, and here is the really clever part, the handoff. That virtual image we just made, I1, it now acts as the object for the second surface of the lens. So as the light leaves the glass, speeding back up into the air, it bends one more time. And this final bend is what brings all the light together to form the sharp, real image that we can actually project or see, right there at point I. It's just a brilliant little two-step process. So now that we've seen those two bends happen separately, what if we combine the math for both? Well, when you do that, you get something incredibly powerful, a tool that's absolutely fundamental to designing lenses. It's called the lens maker's formula.
And here it is. What this formula does is connect a lens's focal length, f, which is basically its core focusing power, its superpower, to just two things. First, the material it's made from, which is that refractive index n, and second, its actual physical shape, which is defined by the curves of its two sides, r1 and r2. But here's the thing you have to get about this formula. This isn't for you and me when we're out taking pictures. No, this is the blueprint. This is what an engineer uses to figure out exactly how to shape and polish a piece of glass to get the precise focal length they need for a camera or a telescope or even your eyeglasses. Okay, but let's be real. Most of us aren't making lenses, right? We're just using them. And for that, we can simplify things a lot. This brings us to a much, much friendlier equation called the thin lens formula. And this just lays it out perfectly. On the left, you've got the lens maker's formula, all those details about the glass and the curves. But on the right, for just using the lens, all we need is this clean, simple relationship between the object, the image, and that one single super important number, the focal length, f. So let's take a closer look at this little powerhouse of an equation. It's just three things. U is the object distance, how far the thing you're looking at is from the lens. V is the image distance, how far the focused picture is from the lens. And F is the focal length. The beauty of it is, if you know any two of those, you can always find the third. Okay, let's try a quick example to see how this works. Say you put an object 30 centimeters away from a lens, and you know that lens has a 15 centimeter focal length. So where's the image going to form? Well, we just plug U equals 30 and F equals 15 into our formula.
You do a little bit of algebra, and what do you know? V, the image distance, also comes out to be 30 centimeters. It's simple, it's powerful, and it just works.
Now, what if math just isn't your favorite thing? No problem. I've got good news. There's a totally visual way to solve the exact same problem. It's a technique called ray tracing, and it's a fantastic shortcut to figure out where that image is going to pop up.
So how does ray tracing work? It's all about following a few super simple rules for a couple of special light rays. Rule number 1. Any ray that comes in parallel to the main axis of the lens, it always gets bent so it passes through the focal point on the other side. Rule number 2, a ray that goes right through the dead center of the lens, it just keeps going in a perfectly straight line. And there's a third rule, but honestly, the best part is you only need to draw 2 of these rays to find your image.
All right, let's see it in action. Look here. You start at the very tip of your object, and you just draw those 2 rays we talked about. And you see where they cross, where they meet up on the other side of the lens? That is exactly where the tip of your image will be. It's like a perfect drawing that confirms exactly what the math formula was telling us. Okay, so now we know where the image is, but what about its size? Is it bigger, smaller, and is it right side up or upside down? This leads us to our next big idea, magnification. And we're going to use it to figure out a really cool magic trick.
And the formula for magnification, M, is actually super simple. It's just the ratio of the image's height to the object's height. And the cool thing is, that ratio is exactly the same as the ratio of the image distance, V, to the object distance, U. Oh, and a quick tip. If M is positive, the image is upright. If it's negative, you know it's flipped upside down.
All right, time for some fun. Let's put what we know to the test with this classic puzzle. A magician takes a glass lens, we know its refractive index is 1.47, and dunks it into a trough of some clear liquid, and it vanishes. It completely disappears. So the question is, what is the refractive index of that liquid? How is that even possible?
And the secret? It's pure physics. The lens becomes invisible because the liquid has the exact same refractive index as the glass, 1.47. Think back to that lens maker's formula we looked at. The whole power of the lens comes from the difference between the refractive index of the glass and its surroundings. If they're the same, that difference is 0. That means the lens has no focusing power. The light just passes straight through as if the lens doesn't even exist. And poof, it's invisible. Okay, we have covered a ton of ground here. We went from the deep physics of how light bends all the way to a cool magic trick. So let's wrap this up by pulling everything together into one simple, powerful toolkit that summarizes all the key ideas.
So here it is, your cheat sheet. The lens maker's formula, that's for the engineer. It tells them how to build the lens. The thin lens formula, that's for us, the users. It predicts where the image is going to be. And finally, the magnification formula tells us how big that image is and whether it's right side up or not. Just 3 formulas that cover the whole story, from design all the way to the final picture.
So let's end with this one thought. Now that you know all the incredible physics that's packed into just a simple piece of glass, what's an everyday object that suddenly seems way more clever to you? Is it your phone's camera, your glasses, maybe just a simple magnifying glass? Really think about it. The world around us is just filled with these tiny, totally brilliant pieces of engineering,